Hello everyone, this is Sherry Sahabi and we are in the data mining class. So far we have learned about kernels and about how to do basic operations in terms of kernels. Now, we also have learned about PCA before and how PCA can find the important directions in our data or axes in our data that represent our data with the most variability while reducing the dimensionality in our data. But as you remember, our PCA was a linear kind of analysis, so it could not understand the nonlinearities in our data. Now that we have learned about kernels, let's see how we can apply the kernel trick to PCA and basically learn about how to find nonlinear patterns or directions in our data using kernel PCA. All right, so let me give you an example of when our original PCA might not work while there is obviously a pattern in the data. So suppose that we are looking at a two-dimensional data set so we have two features, two dimensions, x1, x2, and this is how our data point look like. Okay, you can see a kind of a U shape in our data, right? If I apply linear PCA here, what it tries to do is to find the directions or axes that are linear combinations of x1 and x2 that can represent our data variability. Maybe what we are going to find, our axes are going to have a direction like this and another direction like this. Like this is our U1 and this is our U2 for linear PCA. But obviously what we are seeing here is a nonlinear pattern in our data, right? What we are seeing is that if I can find a curve like this would be the best direction that actually shows the variability in my data. So I want my U1 to look like this curve, and then my U2 would be something like this, right? So these kinds of curves. So PCA in its regular form cannot capture such a thing, but kernel PCA can. So kernel PCA can find this U1 for us, for example, and this other kind of. It can find these kinds of directions. And we will see why I say kind of. All right, so how kernel PCA is going to do that? We said that in kernels, we are going to have a transformation phi of x from x to phi of x. So from the input space to the feature space. And then everything is going to be done in this new representation. Now, phi of x is a higher dimensional representation of x. In reality, we do not have access to phi of x. Instead, we are using the kernel functions that are basically defining the similarity or the dot product between phi of x and phi of y, every pair of data points that we have in this new feature space. And using the kernel matrix, we can learn nonlinear relationships between our data points depending on the choice of kernel, which is basically representative of the choice of our phi of x. So let's see how we can do the kernel PCA. You remember from PCA formulation, what we had was like this. We were working with the covariance matrix of our data in the linear case. And we said, for example, sigma, the covariance matrix, multiplied by, let's say, U1, which is the first eigenvector of our data, is equal to lambda 1 U1. Right? And lambda 1 was our first eigenvalue or largest eigenvalue. And after we found the largest eigenvalue or eigenvector, we could do this for U2. Sorry, this is not working. So U2, etc., etc. So basically, we could put together all the eigenvalues, eigenvectors, and say this whole thing in a matrix kind of representation. So we had sigma, matrix U is equal to diagonal matrix lambda multiplied by matrix U. This was our PCA in the original space that we had. Now, in kernel PCA, what we are going to do is that we are going to work with the covariance matrix of our data in the feature space. So this is going to be our formulation. We will have sigma phi, which is basically the covariance matrix of our data in the new feature space. This is our formulation of the problem. Multiplied by U1, this is the U1, this red U1, so the direction of maximum variance in the feature space is equal to lambda 1 U1 again. Okay, so our goal here is to find the U1 and lambda 1 given our covariance matrix in the feature space. Okay, so let's see how we can find this. Covariance matrix, we remember that the sample covariance in original input space, we could calculate it like this. We said sigma is equal to 1 over n, sigma sum over I equals to 1 to n. So all of our data points, xi transpose, assuming that our data is centered. So as we said before, here we assume, assumption is that we are working with centered data. So assume that everything is centered. That's why our covariance could be written like this. So we basically, our mu is going to be 0. Now in the feature space, what we are going to have is this. We are going to have our sigma phi in the feature space is equal to 1 over n, sigma I equals to 1 to n. Instead of xi, now I have phi of xi, right? Phi of xi transpose, assuming that our phi is centered. Okay, so I can rewrite this eigenvalue, eigenvector decomposition like this. I can say that 1 over n sum of phi of xi, phi of xi transpose u1 is equal to lambda 1 u1. Right, that is our eigenvalue, eigenvector decomposition that we would like to solve. All right. Now, n, 1 over n is a constant, and lambda 1 is also a constant. It's a scalar, right? So I can move it in. So what I have is something like this. I have sigma I equals to 1 to n, phi of xi, phi of xi transpose over n lambda 1, u1 is equal to u1. All right. Now, if I look at this thing, phi of xi transpose u1 is going to be a scalar, right? So this is going to be a scalar, right? So phi of xi transpose is a 1 by d prime. D prime is the new dimensionality of our data in the feature space. It's a 1 by d prime vector. And u1 is a d prime by 1 vector. So what we have is by the phi of xi transpose at u1, we are going to get a 1 by 1 scalar. And n and lambda 1 were already scalars, so this whole thing is a scalar. Let's call this scalar ci, because it relates to phi of xi. So what we are getting here is something like this. We are getting sigma I equals to 1 to n, phi of xi, ci is equal to u1. Sorry. Okay. So what does this mean? This means that we can get to u1, which is the direction of maximum variance or principal component in the feature space, using a linear combination of points in the feature space. Why linear combination? Because it's a scalar multiplied by phi of xi. So basically u1 is a linear combination of phi of xi's that are scaled by ci, right? So u1 is a linear combination of data points in our feature space, right? Okay, so that is very interesting. Let's see if we can use this as we are learning more about our directions. So what we can do is that now that I have this conclusion that u1 is equal to a linear combination of my data points in the feature space, I can replace my u1 in this equation here using the red box equation, right? So let's do that. Let's replace our u1 using that. So what we will get is this. I have summation of I equals to 1 to n phi of xi multiplied by, now I have phi of xi transpose u1, right? So phi of xi transpose, now instead of u1, I will use this sigma summation I don't want to mix I and j, like this I and this I, so I will use j here. J equals to 1 to n phi of xj cj. And that's equal to n lambda 1 u1, right? I just moved 1 over n from here to there. Which is basically this u1 we can also rewrite and just say that this is equal to sigma j equals to 1 to n fix j cj also. All right. So what I can do is that in this bracket here, phi xi is independent of j in this summation, so I can just move it inside. So what I get is summation of I equals to 1 to n phi of xi, summation of j equals to 1 to n phi of xi transpose phi of xj cj is equal to n lambda 1 phi. Let's say this is, we can actually use I here. I equals to 1 to n phi of xi ci. Okay, so why are we doing all of this? It's because our goal, remember our goal when we are working with kernels, is to represent our problem in terms of kernels so that we can show that the kernel trick works for our problem. So for example, we have shown that we cannot calculate the mean of our data points in the feature space using phi of x and kernels, but we can calculate the norm of our mean vector, right? So here we are trying to show everything in terms of kernels. All right, so far, this thing is familiar to me, right? This is actually the kernel between xi and xj. All right, so far I got to some kernel value here. But then I still have this phi of xi here and phi of xi on the other hand, on the other side. But because it's kind of a symmetric thing, let's do a trick. Let's multiply both sides of this equation with a phi of some xl, for example, or xm, let's call it xm, transpose. So I just pick one data point, xm, from all of my data points, and I just multiply both sides of this equation with phi of xm. Okay, it doesn't make any problems with my equation, right? Because I'm multiplying both sides with the same number. So the equation is still the same. But let's see what happens then. If I do that, what I will get is this. I can move xm inside this sigma on the left because it's independent of I, right? So I will have summation of I equals to 1 to n phi of xm transpose phi of xi summation of j equals to 1 to n. I already have this like a kernel xi and xj multiplied by cj is equal to n lambda 1. Again, I can move phi of xm inside the sigma here. Sigma I equals to 1 to n phi of xm phi of xi, ci, right? So this looks nice now. Why? Because, see, I have two other kernel-like formulations here. So this first one is basically the kernel value between xm and xi. And similarly here, I have the kernel between xm and xi. So what I have now in my new equation is this. I have my new equation looks like this. Now that everything is kind of kernelized, it's like this. We have summation of I equals to 1 to n k xm xi summation j equals to 1 to n k xi xj multiplied by cj. Cj is basically a scalar, right? Is equal to n lambda 1 summation of I equals to 1 to n ci k between xm and xi. Okay. So far, we could rewrite our PCA problem, the eigenvalue eigenvector decomposition problem, in terms of kernel matrices. But we haven't said how we are going to solve it yet, right? We don't know what Ci and Cj are. These values, we don't have any idea about those, and we don't know what the lambdas are going to be. So let's see how we can solve this. Remember that when we picked phi of xm was just, m was one number, one data point in our data set, right? So xm is one data point. But our data set has n different data points in it. So xm can be x1, it can be x2, it can be x3, it can be any of these data points between x1 and xn, right? So if I choose different xm values, I'm going to get a different equation here. Why we are doing this? Because we are trying to find the values CIs and CJs, right? Our CIs and CJs, we have n different unknown C's from C1 to Cn. And at the same time, using different data points, xm's, in our data, we are going to have n different system of equations like this one here. So for example, our system of equations are going to look like this. For m being equal to 1, I'm going to have, so 1 to n k of x1 xi sigma j equals to 1 to n cj k xi xj equals to n lambda 1 I equals to 1 to n ci k of x1 and xi. If I choose m equals to 2, I'm going to have another one of these. So it's going to be I equals to 1 to n k of x2 xi sum j equals to 1 to n cj k xi xj is equal to n lambda 1 I equals to 1 to n ci k x2 xi, right? So I can do this until m equals to n, and get this equation that sum of I equals to 1 to n k of xn xi is j equals to 1 to n cj k xi xj is equal to n lambda 1 I equals to 1 to n ci k of xn xi, right? So now I have n different unknown c's, and I have n different equations that are going to give me that I can solve to get to the c's. So basically, I will be able to find a vector c, which is c1, c2, cn, using this system of equations. Okay. So to make things a little bit easier, let's create a notation. Let's say k sub l is equal to the summation of k of xl and xi, I equals to 1 to n. Okay, so that we can, basically we do have these summations, and so that we can represent them more easier. So if I define this, basically k sub l is going to be a summation of a row of my kernel matrix, or a column of my kernel matrix, right? If I do this, then I can rewrite my system of equations, these n equations, like this. I can say that the summation I equals to 1 to n k of x m and xi now ki transpose my vector c there is equal to n lambda 1 k of m transpose c. Okay, how? So here we have a summation over all the j's, k of specific xi with xj, right? So that's going to be equal to k sub I for me, right? And then because I have these cj's, they are going to create this vector c for me. And on this side also, I do have the k of my specific n with all the xi's, so, and with the c's, I'm going to have this one, right? Okay. Now, if I put this whole system of n equations together, what I'm going to have is going to look like this. I'm going to have, this is one kernel matrix, and this is the KL. And then putting all of these together, I'm going to get to this. I'm going to get to K squared C is equal to N lambda 1 K C. Okay. that sounds interesting. It looks like that I could get to an equation that I don't know about C, I don't know about lambda 1. I know K is my kernel matrix, and I know N. Now I want to find C and lambda 1 according to K and N. This equation looks a little bit familiar to us, although it's not exactly what we are looking for, right? So it looks like eigenvalue, eigenvector decomposition, but the difference is that we have K on both sides. But because it is on both sides and it can be shown that it's equivalent to this. Kc is equal to n lambda 1 c. Now we get to an actual eigenvalue eigenvector decomposition. So given k and n, we can easily find c and lambda 1, right? Because this is an eigenvalue eigenvector decomposition. We will know that c is the eigenvector for k, and n lambda 1 is the eigenvalue for k, right? So this way, when we get to k and we know n, we can find c and lambda 1 easily. So the largest eigenvalue for k divided by n will be our lambda 1, and the eigenvector that is associated with that largest eigenvalue would be our c. Okay, so I have found c, I have found lambda 1, but I still didn't get to my u. You remember that we were looking for this vector u, right? We were looking for u. But what we have found so far is the ci's and the lambdas. Okay, so how can I get to the direction? I want to get to the direction. The PCA gives me the axis, right? How can I get to my u? We know that u1 is equal to sigma I equals to 1 to n, because we have it here, right? Phi of xi multiplied by ci, right? So it's phi of xi ci. Now I know what C is. Can I get to U1 from that? Well, unfortunately not. Why not? Because phi of xi is not available. I have C1, C2 until Cn, but I don't have phi of xi. Remember that in kernels, the whole point was that we do not need to transform our data into the feature space. We just can work with the kernels. So I can't really get to this direction UI, or it's not really, it doesn't make sense for me to do that, right? But what can I do instead? You remember that when we did PCA, after we found the direction of our data, the axis, the new axis, what we did was that we projected our data points onto these new axes. And using that projections, then our covariance was 0, and we could work with the data in lower dimensions, right? So now let's see if we can, so we cannot access to the direction U1 or U2 directly, but let's see if we can get to the projections of our data onto U1 and U2 directions. and because we need to work with that data, right? So let's see if we can project our data into direction of U1 instead of calculating U1 directly. So one other thing that is important to not to forget is that when we were doing PCA, we always said that U1 is a direction, an axis for us, and also it is normalized. You remember orthonormal vectors use very orthonormal. So it's normalized such that U1 transpose U1 is equal to is equal to 1, right? That was basically what we had. But I don't have a guarantee that U1 transpose U1 is equal to 1 in this equation. So what we are going to do first, before doing the projection, is to normalize our U1 such that our U1 transpose U1 is equal to 1. How are we going to do that? Well, U1 transpose U1 is basically U1 transpose U1 is basically summation of I equals to 1 to n, j equals to 1 to n, ci, cj, phi xi transpose phi xj, right? And well, this is k xi xj. So basically I can rewrite U1 transpose U1 as C transpose, like all the C's that I have, K, my kernel matrix, and it's UI transpose UI, right? For all i's. And multiplied by C, right? And I want this to be equal to 1, and I want this one also to be 1. So this is my new constraint that I have. But also from here, I have seen that this multiplication of matrix kernel matrix with C is equal to n lambda 1 C, right? Okay, so what do I get? What I'm getting is this. I'm getting that C transpose n lambda 1 C is equal to 1, meaning because n and lambda 1 are scalars, C transpose C is 1, so C transpose C is equal to 1 over n lambda 1. As a result, we get to this, that the norm squared of my vector C is 1 over n lambda 1, so the length of my vector C is equal to 1 over square root of n lambda 1. Okay, so using that, I can easily normalize my vector C just to make sure that my U1 transpose U1 is going to be equal to 1. And this way I can easily project my data points into U1. How did we do the projection? If I want to project my phi of xi to U1, what I can do is that I can say, I can calculate U1 transpose phi of xi, which we know U1 is, we know from here. Oh. We know from here that U1 is equal to summation of phi of xi ci's, right? So basically, it's going to be, let's call it J because we don't want to mix it up with phi of xi. Sigma J equals to 1 to n phi of xj cj multiplied by phi of xi, right? Which is equals to sigma j equals to 1 to n cj phi of xj transpose phi of xi. Nice. We are getting close to our kernel formulation now. So this guy here is now familiar to us, right? It has the kernel form. It's k between xj and xi. That's very nice. So basically it means that the projection of my phi of xi, my data point, onto the first PCA, kernel PCA axis is going to be equal to the summation of j equals to 1 to n cj, the kernel between all the other data points and my data point xi. All right. So now that we can project our data points into the kernel PCA axis, we can easily work with this new data. So this is for the first direction of kernel PCA. For the next directions, we are going to look at the second eigenvector, eigenvalue decomposition, the third one, etc., etc. All right. So what we have learned so far is this. What we have done, let's go over it once more. We wanted to do kernel PCA. So we rewrote the PCA equation based on the covariance matrix of our data in the feature space. Then what we did, we rewrote, we found what the covariance matrix formulation is, and we substituted it into this eigenvalue eigenvector decomposition. And with some algebra, we concluded that our first principal direction is a linear combination of our data points in the new feature space with CIs as the weights or coefficients. So we did some more algebra, and then we got to this formulation that the kernel matrix multiplied by the coefficient vector is equal to n lambda 1 multiplied by the coefficient vector. So from that, we got to this point that, okay, we can find the coefficient vector or weight vector C and the lambda 1 scalar by eigenvalue eigenvector decomposition of the kernel matrix K. Okay, we have found CIs. Now to find the directions, the axis UI, we looked at this equation above and said, oh, because this equation includes phi of xi directly, we cannot calculate UIs based on that. Instead, what we tried to do was to project our data points into the direction UI, and we figured that the projection of our data points in the new feature space onto the first direction of kernel PCA is a basically weighted summation of the kernel matrix between all of our data points and that data point, that specific target data point that we are projecting it. All right. And also we did normalize our coefficient vectors in a way that ui transpose ui to be equal to the unit vector. Okay. So one thing that we didn't talk about is the dimensionality reduction now. Okay, we have found the direction U1 from kernel PCA, we have found the direction U2, etc., but we didn't talk about dimensionality reduction. Now, similar to the dimensionality reduction in linear PCA, we are going to do something like that. You remember this formulation here that we said CIs are going to be eigenvectors of kernel matrix K, and then we have eigenvalues lambda is equal, the lambda i's that are equal to the eigenvalues divided by n. Now, basically, it shows this lambda i's are showing the variance that we get from our data in the direction of the specific principal component that we are looking at. So if I have a if I have U1, the variance along U1 is going to be equal to lambda 1, okay? And which is basically the eigenvalue 1 for k divided by n. Okay, so now that I have all of the variances along all of the principal vectors, for the dimensionality reduction, I can start with the principal vectors or directions or axes that has the smallest variance and start removing those. And I can remove those until I get the required percentage that I'm looking for. So if I'm looking, for example, for 90% variation representation in my data, I start to remove the smallest eigenvalues until I get to 90% or more. Okay. So let's look at the kernel PCA algorithm. What we are going to have as our input is going to be our data D. We are going to have the kernel function, and we are going to have the variance that we are looking for. So at the beginning, we are computing the kernel matrix in line 1 according to the kernel function for all of our data points. And then in line 2, we are going to center the kernel matrix because all the computations that we have done, and I have showed you, it's according to a centered kernel matrix. And we have learned how to center the kernel matrix before. In line 3, we are going to calculate the eigenvalues of K, this kernel matrix, and we are going to use them later on to reduce the dimensionality of our data, right? Then in line 4, what we are doing is that we are calculating the eigenvectors of kernel matrix K. Remember that unlike linear PCA, these eigenvectors are not our axes or directions of new directions of our data in the new feature space. We cannot calculate the new directions of our data into the new feature space. These eigenvectors are going to be our coefficients for the directions of our PC, like principal components in the new feature space. Okay. Then in line 5, what we're doing is that we are dividing our eigenvalues by n to compute the variance for each component or for each direction. And in line 6, what we are doing is that we are dividing our coefficients by nu I to make sure that our eigenvectors, principal components are orthonormal to each other. So ui transpose ui is equal to 1. In line 7, what we are doing is that we are calculating how much each of our principal components are adding to the variance of total variance of our data that we are going to represent by them. So it's basically the fraction of total variance that we are going to keep if we keep that particular principal component and the ones that are more important than it. And eventually, in line 8, we are going to choose the smallest number of principal components that give us the minimum variance that we needed, alpha, that we had it from the input of the algorithm. And then we are going to just remove all the coefficients, CIs, that are larger than R, the first R's, or the reduced dimensions. And in line 10, we are projecting all of our data into the new axes, new UIs, without calculating the UIs, but with just calculating the CR transpose kernel matrix for each of our data points, right? The kernel row for each of our data points, and that is going to give us the reduced dimensionality of our data. Okay, this is what we have done in our calculations also. So let's look at an example. Again, suppose that this is our data in the original space. You see that we have this kind of a U-shape thing in our data. If we run linear PCA though, what we are going to get is two lines as our directions, right? A U1 and U2 that are linear combinations of X1 and X2. So U1 is like this, U2 is like this. So if we represent our data in terms of U1 and U2 instead of X1 and X2, it's as if we are just rotating our data a little bit. So our data is going to be rotated and it's going to still have this curvy shape, but in the directions of U1 and U2. Now, if we apply kernel PCA on this data using a homogeneous quadratic kernel, which is basically k between x and y is equal to x transpose y squared. Quadratic because this shape looks quadratic to us here. And so we think that it's going to give us a good result. Then the directions, you can see the directions U1 and U2 here. What we are seeing is that basically one direction, you can see that according to these circles, it's as if this direction is capturing this variability in our data, and this other direction U2 is capturing this variability in our data. And if we project our data into these two directions and represent them in terms of these two directions, see what we are getting is not that curvy shape that we had before. It's kind of more linear like. All right, so that's how kernel PCA is going to be useful for us.